Electromotive force and internal resistance. Physics for everyone welcomes you. And let us learn about electromotive force. Next, internal resistance of the battery. Next, determination of internal resistance. Next, power delivered to the circuit of resistance R. Finally, potential difference V across the terminals of the battery. Let's start with electromotive force. Here you have a chemical cell with two electrodes connected with a high resistance voltmeter. The positive electrode, the negative electrode, and this cell contains the electrolyte. A battery or cell is called a source of electromotive force, EMF. The term electromotive force is a misnomer since it does not really refer to a force but describe a potential difference in volts. This volts equals to electromotive force epsilon. The EMF of a battery or cell is the voltage provided by the battery when no current flows in the external circuit. A is the positive terminal, B is the negative terminal. There is a force that separates the positive charge and negative charge in the electrode. This Fn is a non-electrostatic force acting inside the battery. Fn moves positive and negative charges towards the terminals of the battery. Fn depends upon the source cell. It depends first on diffusion process, second on varying electrolytic concentration resulting in chemical reaction. More is the concentration, faster the chemical reaction, lesser the concentration, slower the chemical reaction. Now, these positive and negative charges separated by this non-electrostatic force inside the battery. Because of the separation of the charges, we have a electrostatic force Fe that acts from the positive electrode to the negative electrode. Because of the separation of positive and negative charges, an electric field E is set up between the terminals, resulting in the electric force Fe. If Fn equals Fe, no further separation of charges takes place. The work done by Fn per unit charge is known as EMF of the battery. The work done by Fn per unit charge is known as the EMF of a battery. Epsilon equals Fn d by Q. Let us replace Fn by Fe because nothing is connected between the terminal. So Fn equals Fe. So epsilon equals Fe d by Q. Epsilon equals, instead of Fe, we can write Q times E d by Q. Q cancels, we get epsilon equals Ed. Ed is nothing but the potential difference V. So epsilon equals V. When the terminals are connected by a conducting wire, right, there is a current setup here. Fe moves this electron through the wire, whereas Fn separates the charges in the electrodes. So, there is a potential difference maintained between the terminals of the battery. Internal resistance of the battery. Here you have a circuit A and B connected through a external resistance R. Internal resistance of the battery. Because of this external resistance, there is a current setup in the circuit, flows from A to B in the external circuit. Within the cell, it goes from negative electrode to positive electrode. Right? In the external circuit, this current is due to flow of electron. Inside the cell, the current is due to flow of ions. The position offered by the electrolyte of a battery to the flow of current between the electrode is called internal resistance of the battery. The opposition offered by the electrolyte of a battery to the flow of current between the electrode is called internal resistance of the battery. Internal resistance R of the battery depends on 1. Nature of the electrolyte and concentration of the electrolyte are proportional to C. Next, distance between the electrode. More is the distance between the electrode, more will be the internal resistance or proportional to D. Next, the internal resistance R depends upon the area of the electrode. More is the area of the electrode, less will be the internal resistance R proportional to 1 by A. Next, internal resistance R depends upon the temperature of the electrolyte or proportional to 1 by temperature. More is the temperature, less will be the internal resistance. A freshly prepared cell has low internal resistance and it increases with aging. Determination of the internal resistance small r. Here you have a circuit. This contains a cell, a battery with EMF epsilon and with an internal resistance R that is shown in the circuit. Actually, this internal resistance is available inside the cell. For our convenience, we have shown just on the right hand side of the EMF epsilon. And this cell is connected to a high resistance voltmeter that reads a voltage V prime. The circuit connections are made as shown in the figure. The EMF of a cell epsilon is measured by connecting a high resistance voltmeter across it without connecting the external resistance R. Since the voltmeter draws very little current for deflection, the circuit may be considered as open. Hence, the voltmeter reads gives the EMF of the cell. We can say V prime equals epsilon. Let us write this close to the diagram. If V prime equals epsilon. Let us redraw this diagram once again. Now, let us include the high resistance between the two terminals of the cell. R is the resistance, external resistance. Now, there is a current setup in the circuit. I is the current setup in the circuit. Then external resistance R is included in the circuit and current I is stabilized in the circuit. The potential difference across R is equal to the potential difference across the cell V. The potential drop across the resistor R is V equals I times R. Let us write V equals I times R close to the diagram. Next, due to the internal resistance R, the cell due to the internal resistance R of the cell, the voltage drop across the external resistance V is always less than the EMF of the cell epsilon. It is because certain amount of voltage IR has dropped across the internal resistance R. So, V equals epsilon minus IR. So, the EMF of the cell is the sum of the potential difference across the external resistance and the internal resistance. V equals epsilon minus IR. Then V equals epsilon minus IR. Let us write IR equals epsilon minus V. Right? We have the previous equation V equals IR. Let us change the left hand side and right hand side. So we can say IR equals V. Divide one equation by other, we get I small r divided by I capital R equals epsilon minus V by V. From here, we can get the internal resistance. An equation for internal resistance R equals within bracket epsilon minus V by V multiplies R. Since epsilon, V and R are known, internal resistance R can be determined. Power delivered to the circuit of resistance R. Power delivered to the circuit of resistance R. The same circuit has been redrawn here. Good. For a battery of EMF epsilon with an internal resistance R, the power delivered to the circuit of resistance R is given by a formula P equals I times epsilon. Let us replace this epsilon by V plus IR. Then we take this we write this V, voltage drop across the resistance R, as IR. We get P equals I times within bracket IR, that is I capital R plus I small r. P equals I square R plus I square small r. I square capital R is the power delivered to the electrical device, that is the external resistance R. I square small r is the power delivered to the internal resistance. And we very well know that for a good and a very fresh battery, the internal resistance R is very small. So I square small r is very small compared to I square capital R. Almost entire power is delivered to the external resistance. Potential drop V across the terminals of your battery. Potential difference V across the terminals of your battery. First, let us consider discharging of your battery. Here, there is a battery that delivers current to the external resistance R. When battery supplies current, we can say V equals VA minus VB, which is equal to epsilon minus I times small r. Let us consider this equation is a general equation, and we very well know that the potential difference across the external resistance R, V, is always less than the EMF of the cell epsilon, because there is a potential difference across the internal resistance small r, that's IR. V equals VA minus VB equals epsilon minus IR. Secondly, charging of your battery, that can be done by an external source, a DC source. Now we deliver current to the chemical cell, to a battery. When battery is taking current, V equals VA minus VB equals epsilon plus IR. Good. V is greater than epsilon, then only the battery can be charged. When the battery is open circuit, look at the diagram, there is nothing connected between the terminal A and B. It's called open circuit. When battery supplies no current, we can write V equals VA minus VB equals epsilon minus, instead of current, we written 0 into R. So the potential difference across A and B simply equals the EMF of the cell epsilon. When the battery is short circuit, that is external resistance is 0. A and B connected by a very good conductor, it gets short circuit. I equals, the current here, I equals epsilon by R. Let us go for the general formula. V equals VA minus VB equals epsilon minus IR. Let us replace the current I by epsilon by small r. So we get V equals VA minus VB equals epsilon minus, in the place of I written epsilon by R times small r. So small r cancel, we get epsilon minus epsilon equals 0. So potential difference across A, B becomes 0. Thank you, children.